back in 1905, Einstein realised that space and time are not separate, but they're woven together into something that's often called the fabric of the universe, or more technically space-time. But we now suspect, or at least we have a theory, that space-time emerges from something deeper, which is just basically quantum entanglement. So we think that there is a description of our universe which is just bits of information, basically, or qubits to be more technical, quantum bits of information that are entangled together into some sort of network, so space and time don't exist in that network, and then space and time emerge from that deeper theory. This is cutting-edge physics, but it's one of the pictures that we have for what space and time might be.
Europa, Jupiter's moon, is a prime candidate for a habitable world. In that, what we know, almost certainly, I'm always, the people who I know who work on the mission say, don't say we know, we're almost sure there's a saltwater ocean below the surface. I think it's pretty indisputable now, so we're pretty sure it's there.
Yeah, but whatever is the skepticism, what would it be were it not a global oceon?
Yeah, it's very difficult to be, because, and that's from many measurements.
Was it made of ammonia? I mean, there's not, you know, water molecule is not rare.
Yeah, so it looks like salt water. Almost
and we have a lot of comparative planetology with, is it the Arctic, when it freezes over, you have these chunks of ice that will break and refreeze and readjust, and you can compare the images and you'd think you were looking at the frozen Arctic.
Quantum mechanics lies at the heart of transistors. Okay. So the phone that people are using to watch the stuff about quantum healing operates on the principles of quantum mechanics.
Really?
That's how transistors work. And we call this a wave function, and it's something to do with probability of finding the thing somewhere. But there are different interpretations of that, and we don't fully understand the theory, but it does work, because your phone wouldn't work if we didn't understand quantum mechanics. And then there's quantum computers, which we're beginning to develop now, which are potentially very powerful things. And there's quantum teleportation, which is teleportation. It actually works, you know, with photons. The universe is stretching or shrinking. So the fabric is stretching or shrinking. Either way, if it's stretching, then that implies everything was closer together in the past. If it's always been stretching, right? So that means everything's close, which looks like an origin to the universe. And if it's shrinking, of course, it looks like there may be an end. That implies there may be an end to the universe. So either way, I think Einstein's theory, it's quite difficult to have an eternal universe in Einstein's theory. And he didn't like that for the reasons I think we're talking about. If you have an origin, you have to start saying why. What is that thing? What does it mean to have a beginning? And it turned out that experimentally, in the 1920s, Edwin Hubble discovered that the universe is expanding. And so that once you've got that measurement, and again, I talk about this in the show, we have those measurements now for thousands and thousands and thousands of galaxies. So we have this whole map of how the universe has changed and evolved over time, experimentally. And then with Einstein's theory, you can figure out when everything was on top of each other, which is 13.8 billion years ago. So you have this question of an origin. But just to say, it's not being uncomfortable. It goes back to what you said about being terrified. It's not unnatural to worry about that, what it means to have an origin to the universe, because Einstein didn't like it, right? He was worried about it, although he accepted it ultimately, because that's what the evidence tells you. Now, I should say, now that we still don't know what it means, that an origin. An origin in time, was it really the beginning of time? Stephen Hawking and many others have thought about these no boundary things and all sorts of things where you don't really have an origin in time. We don't actually know what time is. I tend to say that we don't know. Space-time, we talked about before, may well come from something else, which is deeper. We don't have the deeper theory yet. We have ideas. It's called quantum gravity. Until we have those deeper theories, then we really talking about the origin of the universe is very difficult.
For example, there's something called the inflationary multiverse. So one of our best theories of how our universe got to be the way that it is that before the Big Bang, then space and time still existed, and space was stretching very fast. It's a theory called inflation. And then that period of time draws to a close. So the expansion rate, this incredibly fast expansion rate, slows down, and kind of the energy driving it collapses, changes form or state, and that's what we call the Big Bang. So the Big Bang is the end of inflation. Extensions of that, called eternal inflation, say or suggest that maybe that collapse at the end of inflation, maybe it doesn't all stop at once. So you're to picture patches of this rapidly expanding space that are sort of collapsing and making big bangs, which make universes. And so that the process is called eternal inflation, because for all we know, it could have been going on forever in a sense, and would be going on now if that was correct. So we would just be a bubble in this sea, an infinite sea of universes, of which we're a single bubble, and that's called the inflationary multiverse. Quantum mechanics does appear to suggest that really there are an infinite number of universes. So every possibility for every interaction that happens has a probability of it. It's like rolling a dice, and you could say, well, I roll a dice and it comes up a 3, but it could also be a 2 or a 4. And basically, the many worlds interpretation of quantum mechanics is that there's a universe in which every dice roll happens. So you get an infinite number of copies of you, for example, in this inflationary multiverse, not the inflation, the many worlds interpretation of quantum mechanics.
Consciousness is, I think, and it's becoming very topical because, of course, AI and the potential development of artificial general intelligence, we're not there yet, but AGI, raises this question of what intelligence, what the experience of being human is. And so there are different, I think there are 2 categories of emergence people speak of. Actually, Sean Carroll, if you had him on the show, he's got about 5 in a recent paper. He's got loads of category 2A and 3B or whatever.
Okay.
But broadly speaking, people think of weak and strong emergence.
Okay.
So weak emergence is what I think virtually every scientist would, certainly a physicist would say consciousness is, which is very complicated, the most complicated emergent phenomena we know of in the universe, I would say. But it comes from the underlying laws. So you could model it with a sufficiently powerful computer. You could imagine modeling how the human brain works. I think most people would accept. There is also strong emergence, which is somehow the phenomena you see is not, you can't simulate it from the underlying laws. There's something else going on. Now, I would not subscribe to that. So I would say consciousness is interesting because it's weakly emergent. It emerges from this thing, the brain. How, we don't know. This thing, the Higgs particle, is really fundamentally different. So there are different ways of thinking about it, but my favourite way currently of talking about it is that it's about this weak nuclear force again. So we talked about the weak force.
Yeah.
And I said the reason all these neutrinos miss your head, 7 billions of them going through your head and you don't get a headache, is because it's very short range. Why is it short range? Well, it turns out that is the answer. The Higgs particle was kind of invented, really, theoretically, to give an answer to that question. And it's really fascinating. And it's partly, my favourite way at the moment is, do you know superconductors? So there are these things called superconductors which don't have electrical resistance. So you can build these remarkable magnets that have no resistance, and they're powerful magnets. So the universe is a bit like, it's like we're living in a superconductor. And what the Higgs field, this Higgs thing that permeates the universe does, is it allows that force, or makes that force short range. And it's very analogous to the way that electricity and magnetism work inside a superconductor, basically. So it is part of the explanation for why this force is short range. The way that I like talking about it now is that it is like that we live inside a giant superconductor. So you have Kepler, Galileo, it's shortly after Copernicus, just before Newton, decades before Newton. And so that is the moment, really. And it is almost a moment, many historians would agree. There's obviously things happened before, but it's the time when we started saying we can look at nature. So Kepler was interested in the motion of the planets in the sky, and he figured out around 1610 that the planets move in ellipses around the sun from the data that had been acquired. So it's the time when we start using data to build models of the world. That didn't really happen before around 1600. Not in that way, and certainly not in the way that Newton did it in 1687. So that idea that you start out, doesn't matter what you think. I mean, Kepler had all sorts of strange ideas about platonic solids and all these things, and which were really based on Greek ideas. And the cosmology at the time was Aristotle's cosmology, that the Earth is motionless at the center of a finite universe. That all went in a few decades, around 1600, because of observations of nature. So that's a big change. And many historians argue that that's the beginning of the modern world in many circumstances. So we're just sitting here now. The Artemis 2 spacecraft has just gone around the moon and landed back on Earth.
Yeah.
That trajectory, which is quite remarkable if you look at it, the way that the moon, have you seen those graphics online where the moon's coming and the spacecraft goes around and comes back, and it landed within about a mile, I think, of where it was supposed to land in the Pacific Ocean. That's Newton's laws that are used to do that.
Yeah.
You don't need relativity, so you don't need the more complex model. And so we discover those. We've not discovered anything smaller than that, by the way.
Is it because you don't have enough energy to bust up a quark?
Yes, or to resolve what's inside it, let's say, to build a microscope.
Because right now, the inventory of fundamental particles includes quarks.
Yeah.
So somebody saying that's fundamental, which sounds a little like the Greeks saying atoms are fundamental.
Oh no, well, they won't be fundamental. You're absolutely right. But they look point-like from the point of view from the energies that we can generate today. But that's one side of particle physics. So we've been exploring the structure of matter. I mean, you think about what a collision is. So let's say you collide, as we did in my PhD, electrons and protons together. So you get an electron beam and a proton beam, and you smash them into each other. What's actually happening? What's actually happening is, one way that the collision can happen is that the electron can emit a photon, which is a particle of light. And the particle of light goes and it hits the proton. Now, the wavelength of that light, which is telling you how small a thing you can see, is proportional to the energy of the thing. That's how hard we're smashing the things together. So the faster you smash them together, the faster you smash together, the higher the energy, the smaller the wavelength. So the smaller the things that you can see. So that's a way of thinking about particle collisions. So it really is a microscope in that sense. Okay. That analogy works. What it means to have an origin to the universe, because Einstein didn't like it, right? He was worried about it, although he accepted it ultimately because that's what the evidence tells you. Now, I should say, now that we still don't know what it means, that an origin. Mm-hmm. An origin in time, was it really the beginning of time? Stephen Hawking and many others have thought about these no boundaries things and all sorts of things where you don't really have an origin in time. We don't actually know what time is. I tend to say that we don't know. Space-time, we talked about before, may well come from something else, which is deeper. We don't have the deeper theory yet. We have ideas, it's called quantum gravity. Until we have those deeper theories, then we really talking about the origin of the universe is very difficult. So it's fascinating, and it's current research. So I say in the show, and I say at the end of the show, and it maybe if there's one moral to my life show, is that we don't know is the most powerful phrase in our language. Because what it means, if you say we don't know, is there's new knowledge to be gained. And if you don't accept that there's new knowledge to be gained, there is no progress. So progress, our civilization rests on people realizing that we do not know everything. Right? It's the most important thing. And it's also very difficult for people. You see it everywhere, right? People don't like to say, I don't know. But there's no science without that.
But you say, we don't know, but then we imagine things and then we test them. Yeah. And then we find out if the test isn't right, the idea is bad. If the test fits in, then the idea is good.
It's Richard Feynman. He said that. And he said it's not even imagine, it's guess. I remember Feynman saying it in a lecture.
Yeah.
He said, we guess, don't laugh. And everyone laughs. And he goes, don't laugh.
So do you guess?
But we guess.
I mean,
Yeah, we that's what theoretical physics is, right? You guess. He just said, don't make it any. Well, you guess about. Obviously, it's an educated guess, but you make a theory, which is a guess, and then you see what the theory predicts, and then you have to go and test it. And as Feynman very famously said, if your prediction disagrees with experiment, it is wrong, and it doesn't matter who you are or how famous you are or how many titles you have. If your theory disagrees with experiment, it is wrong, and that's it. That's it. That's all. Actually, in the show, so my live show, it starts with Johannes Kepler, on the Charles Bridge in Prague, 1609, as Kepler wrote, New Year's Eve, 1609. He was walking across the Charles Bridge to a party, and he was looking at the snowflakes landing on his arm, and asking questions about the snowflakes, why they're the shape that they are, why they have 6 corners. And he wrote a beautiful book, which you can still get, called The 6-Cornered Snowflake. And I recommend it very strongly.